So in this section, we're going to look at compounds, which are mixtures then of two or more types of elements into a distinct ratio. So for example, NaCl is a very common compound that's table salt or just salt. And table salt is always 1 sodium for every 1 chlorine. Now we're also going to look at some other weird things in this section. We talked a little bit about the atoms and how there's a number of protons. We're going to see that some of the elements exist in more than one of them together. All right. And buckyball C60 is an example of that. It's literally just 60 atoms kind of in a soccer ball formation. Ozone, which maybe you've heard of in the upper right hand corner, is 3 oxygen atoms. And that's quite different than the kind of oxygen we breathe. And we'll talk about that later. Finally, in the lower right is an example of an organic chemistry molecule. That's methane. That's CH4. We're going to talk more about those kind of compounds in Chem 222, but I am introducing it here just to show you the variety of things that you can get. Now remember that the smallest piece of a compound is a molecule, all right? And an ion is if you have something with fewer or more electrons than usual. And we'll talk about that in this section as well. So compounds are a combination of 2 or more elements in definite ratios by mass. What that means is that table salt, for example, is NaCl, and it's always NaCl. It's never NaCl2 or Na2Cl. The next part is important. The character of each element is lost when forming a compound. So for example, we saw a video at the end of the last section when you take pure sodium and pure chlorine, which would both kill us really quickly, it makes sodium chloride, which is table salt. So you can absolutely consume table salt, but you wouldn't dare consume sodium and chlorine. So the elements or the big things you start with are quite different than the compounds. And then just like we saw that an atom is the smallest part of an element, a molecule is the smallest part of a compound. If you break apart the molecule, it will no longer have the same properties as the compound, and it might do other cool things, but not what we wanted here. Here's an example of a formula, and we'll see lots of these coming up. Now, this is for a compound called glycine, and glycine is C2H5NO2. And what that formula means is that there are 2 carbons, 5 hydrogens, 1 nitrogen, and 2 oxygens. So notice that the number of atoms is placed in the lower right-hand corner. There's a picture of glycine, and that one's kind of color coordinated. You can see that the kind of blackish, grayish kind of atoms are carbon. The white atoms are hydrogen. Oxygen is a red, and nitrogen is a blue. And again, we'll see more of this here coming up. But the problem with some of these formulas is there's more than one way to write them. Now, the picture down there shows how the atoms are actually oriented in space. So scientists will sometimes, instead of writing it C2H5NO2, they'll write it H2N CH2 COOH. And you can see they're trying to kind of follow the pattern on the molecule. So this part right here is the NH2, which is first. This is the CH2. Then there's a COOH. All right. So that's another way that sometimes people represent these. By the way, if you're noticing that this C and O has a different kind of connection, like 2 lines instead of 1 line, we're going to talk about that more in Chem 222. That's called a double bond. All the other bonds on this molecule are single bonds, and we'll see what that means future times. Chemists can also write that same formula in like 2-dimensional space. And this thing right here is just called a structural formula. And that's another way to do it. Now, a structural formula is nice because it kind of shows a little easier how the atoms fit together. It does show, for example, that carbon-oxygen double bond. But if you're using a program like Microsoft Word or Google Docs, which is kind of the dominant word processors right now, it's difficult to draw something like that. You'll need something like Illustrator or some program like that instead, or a special program to write chemical formulas, which do exist. So there's lots of different ways to write these. A structural formula is sometimes called a condensed formula, and all these ways are legit. Most of the time, we're going to write our formulas like this because they're compact, all right? But there are uses for the expanded versions as well. Here's, again, kind of an overview of some other ways to show. A drawing of glycine in a two-dimensional kind of representation is right here. This one down here on the lower left is called the ball and stick model. In Chem 222, well, if we're meeting face-to-face, we will use a model kit, and the model kit's essentially use like a ball and stick kind of system, and it shows the geometry, which will be important to us later. And then if you're more of a physicist or a chemical physicist, the space filling model is actually the best way to represent it because it shows how the electrons overlap. Space filling, although they are probably the most accurate, are kind of difficult to see. So they're not used that much in just traditional kind of chemistry, but it does have uses sometimes too. So these are all ways of showing what glycine is. Here's another example. This is ethanol, another compound. Ethanol is actually drinking alcohol. Now, ethanol, if you look in the lower right corner, is CH3CH2OH. And all of these are ways to show that same thing, but with ball and stick space filling, or what's called a perspective drawing. But notice that they all have an OH. The upper two have a red oxygen, so it makes it easier to see. And then you have the CH2, CH3 parts on the end. Perspectives are sometimes used as well. They used to be really popular, but now the ball and stick with the right kind of programs are easier to make, but you will sometimes see it. In a perspective drawing, the little dotted lines, those are hydrogens that are going into the page of the screen, if you will, into the piece of paper. And these little kind of darker lines are called wedges. Those are coming out of the screen or out of the piece of paper, depending on what you're looking at it. So in this CH3, only this CH is actually in the paper. And then the little dotted dash line, that's going back into the screen. The wedge here that I put an arrow next to would be coming out of the screen. It's trying to show three-dimensional information. Here's different formula types too, and this will be helpful to us now coming up. Now, water, as we talked about earlier, is H2O, and that means 2 hydrogens and 1 oxygen. And water is going to be always H2O. It doesn't ever change its formula. Now, that's called a molecular formula. All right, that's kind of like a condensed version of the formula, and the molecular formula just says literally how many atoms are in the molecule of water. An empirical formula is the smallest whole number ratio of atoms. So whole number in chemistry almost always means don't have fractions. You can see here that water has 2 hydrogens and 1 oxygen. We can't break that number down by any farther. So 2 divided by 1 and 1 divided by 1, still H2O. Water has an empirical and molecular formula that's the same. We'll come back to this here in a little bit. Structurally, however, the oxygen's actually in the middle of the molecule and hydrogens are on the outside. So the structural version of water is HOH, and that'll be helpful to us too. Now, let's go back to that molecular empirical thing again. Hydrogen peroxide, the H2O2 that killed the chemist in that stupid joke I had earlier, that literally, the molecular formula is H2O2. So now you see maybe the joke and stuff. Oh boy. Anyway, the empirical formula is the smallest whole number ratio of atoms. So in hydrogen peroxide's formula, if you divide both of those numbers by 2, you're still going to get a whole number. So you divide both of those 2's by 2's, that's going to give you the HO. So empirical formula, smallest whole number ratio of atoms. And some molecules, like hydrogen peroxide, do have different empirical and molecular formulas, and some molecules, like water, share the same molecular and empirical formula result. The molecule itself looks like an HOOH when you figure it out, and that's something we'll do in Chem 222. So HOOH would be the structural formula, like what it kind of looks like in space. Ethylene, ethane, ethanol, and dimethyl ether are going to be great examples to take this a little bit further. Let's look at ethylene first, which, by the way, keeps your bananas fresh while they come up from Central America to North America. But anyway, C2H4 is the molecular formula. And if you would divide both of those numbers, the 2 and the 4, by 2, that's going to give you an empirical formula of CH2. So ethylene has an empirical formula of CH2. Ethane sounds kind of like ethylene, but it is different. It has more hydrogens. It's C2H6. So if you divide both the 2 and the 6 by 2, you're still going to end up with whole numbers. That's why ethane has an empirical formula of CH3. And you can see there how ethane kind of has an H3C and then another CH3 on the other side of it. Now, ethanol and dimethyl ether, the last two examples, have the same molecular formula. They're both C2H6O. And because of the one oxygen, you can't make a one any smaller. The molecular and empirical formulas for those are going to be the same. But look at the structural formulas now. Ethanol has an H3C, and then it has a CH2 and an OH. So again, that's what it looks like. H3C first, CH2 in the middle, if you will, OH on the end. Dimethyl ether has an H3C, it has an oxygen in the middle, and a CH3 on the end. So ethanol and dimethyl ether have the same molecular and empirical formulas, but their structural formulas are quite different. So you can see hopefully here why all of these types, formula types, have uses in chemistry, and they're all going to be really important as we go through these sections. Okay, here's an example of a kind of question you might see. What's the empirical formula for P4O10? All right, and again, the idea here is you want to get the smallest whole number ratio of atoms, and whole number is important. If you divided the 4 and the 10 in that formula by 4, you'd end up with P1O2.5, which is D. But I'm going to let you know right now, chemists really do not like using fractions. No decimals, no fractions. So that wouldn't be a good choice in chemistry. Instead, if you take the 4 and the 10 and you divide them by 2, you would get P2O5. And those are both whole numbers. That's going to be the empirical formula. Again, empirical formula is smallest whole number ratio of atoms. Don't go to fractions. That's really important.